Hello, this is Cal with section 5.3, diagonalization. That's a word you're probably going to be able to need to say. Diagonalization. Okay, this one is the biggie. This is probably the hardest section left in the course, because chapter 6 really isn't too bad. So, go ahead and read the intro paragraph. Read example 1, which is a little bit motivating. The idea is that it will sometimes be useful, not really in this class, but in a lot of applications, it will sometimes be useful to be able to compute powers of matrices really quickly. And if we're able to factor our matrix A as PDP inverse, where D is diagonal, then it's really easy to compute powers. And example 1 and example 2 will walk us through how that works. These are kind of cool examples and are, well, one sort of weak motivation for what we're about to do. There are other ones. All right, over here, a square matrix A is diagonalizable if it is similar to a diagonal matrix. That is, A is PDP inverse for some invertible matrix P and some diagonal matrix D. You need to know that definition. Theorem 5 is the diagonalization theorem, and it really tells us how to diagonalize a matrix. Being able to make this decomposition has everything to do with eigenvalues and eigenvectors. Now, go ahead and read what an eigenvector basis of Rn is. Don't worry too much about the proof, unless you want to. But what I do want you to do is work really carefully through example 3 in this section called diagonalizing matrices. This is going to walk us through the process of diagonalizing a matrix. Step 1 is to find the eigenvalues of the matrix. To do that, we compute the characteristic polynomial, factor it, and solve. Taking note, by the way, of the multiplicities of our eigenvalues. Step 2 is to find a basis for each eigenspace of A. So once we know the eigenvalues, we can find a basis for each eigenspace. If you don't know how to find a basis for an eigenspace by now, you're in trouble. Make sure you go back and figure that out. Step 3 is to take those eigenvectors we found in step 2 and shove them into a matrix. And step 4 is to construct a diagonal matrix from the corresponding eigenvalues. So the order here should correlate to the order up here. And that's really it. I just made it sound simple. There's a lot of computation involved. The book also gives you a handy way to check whether you've done the work without actually having to invert the matrix P, which is nice. So, example 4 is just going to be another example of this, but this is going to be one where you cannot diagonalize the given matrix, and you'll kind of see what falls apart here. Theorem 6 says, if I've got an n by n matrix with n distinct eigenvalues, it's diagonalizable. That's a special case. That's not the only way for a matrix to be diagonalizable. Example 3 should, be a counterexample to that idea. This blurb, matrices whose eigenvalues are not distinct, and Theorem 7 is really the key to understanding diagonalization. I would read through this theorem very carefully, and I would go through the accompanying example number 6, and I would try to figure out what that means in terms of what you're looking for to determine whether a matrix is diagonalizable. This section should really take some careful work with your reading. I would expect to spend a lot of time on this one. It's a pretty tough one. Theorem 7 really is the key, so spend your time on that, okay? And that's all I've got.